The peaks around Mont Blanc comprise basement rocks. That's the crust upon which Mesozoic sediments were once deposited that have now been uplifted to way over 4,000 meters above sea level, creating these spectacular landscapes. Jagged peaks. The Mont Blanc range, the most dramatic landscapes in Europe. And here are the basement rocks without snow on them in the Ecrins, further south in the Western Alps. A glacier just peeking through. And the jagged peak of La Meige. So these are landscapes made by the crystalline basement, the crust of the European margin of Tethys, stacked up to create the Alps. And we're looking at basement rocks in the so-called external zones of the Alps, and they form these external basement massifs, the pink pieces on these maps. The Mesozoic cover, which overlies the basement, forms the subalpine chains and Jura, shown in the green and blue on this map. So we're going to look at the structure of the so-called external basement massifs, and we want to understand the Alpine structure, the structure that developed as the Alps were made during the later part of the Tertiary. In this presentation, we're going to be looking at how ideas have evolved as to what that structure might be. And we can use these to get a general understanding of how basement, the continental crust, becomes involved in orogenic belts, how it shortens, and what the underlying crustal structure might be. And we're going to concentrate on this area here, the Ecrins, otherwise known as the Pelvoux Massif, which forms this bulb-like outcrop pattern at the southern end of the main train of the basement massifs. And like the Mont Blanc area, it can create some pretty spectacular topography, and it still rises to over 4,000 meters above sea level. Now, on the simplified map, I've just coloured in the basement in pink. And in many accounts of orogenesis, the basement, the continental crust, is considered as a rather homogeneous material. But that's not the case. So let's look at the detailed map represented by the boxed area. Here it is. And the Mesozoic cover units are shown in blue, the Tertiary in orange, and the basement has got all that variety in it. And you can see from the key that it's pre-Triassic in age, and it ranges in age back from the Carboniferous and metasediments in the Lamure outlier, which includes some coals, some granite, some metabasic rocks, which are ophiolitic, metasediments, which could be sammites and peelites, some meta-igneous amphibolitic gneisses, and also some migmatites. We're going to look at these in turn. So the photograph we've got here is an example of the late Variscan granite. But much of the outcrop area comprises these migmatitic gneisses. Together with metasediments, there's a rucksack on here for scale, that blob, and the pale leucogranite sheets that are layered with peelites and sammites, in other words, metasedimentary units. And these pick up a foliation, seen here in outcrop. So a variety of different rock types comprise the basement. Okay, well, this will become important later on. What we're going to be looking at chiefly is a transect across this region, along the line of the blue strip, which broadly follows this valley line, which deeply cuts down into the landscape and holds the Romanche River. It's a really classic transect in Alpine geology, much studied and visited over many decades. And you'll see why shortly. So we're going to look at how this cross-section has been interpreted over the years. And here are an array of examples of these different interpretations. We're going to look at each of these in turn, starting with this section here drawn by John Ramsay in 1963 for a field guide through the region. And Ramsay interpreted the basement cover relationships. The basement here is in pink and the Mesozoic cover rocks are shown without a colour. Well, he interpreted these structures as being interfacial buckles, rather like this sort of structure which we see in outcrop, where the basement is considered to be competent and the incompetent sedimentary cover forms pinched-in synclines. For example, beneath Bourg-d'Oisans, there on the cross-section. So for Ramsay, it was all about folding. Somewhat later, the same cross-section or part of it was interpreted like this by Alistair Beach in the early part of the 1980s, and by then there were many attempts to apply thrusting models to the Alps and other parts of the world. So for Alistair Beach, the basement cover relationships were strongly thrusted, and these thrusts climb up into the blue Jurassic rocks on the cross-section. That's the line of cross-section shown by Alistair Beach's section. And while we're talking about thrusts, well, there's certainly thrusts in the landscape here, and some of them are pretty spectacular. And if you look at the map, these thrusts must change geometry from north to south. So consider La Meige thrust, picked out here by the black arrows, and it must climb section laterally as it goes from the Ecrins basement into the Dauphinois Jurassic rocks shown by light blue colour on the map. And it's pretty evident in the landscape. So here we are looking east onto the mountain of La Meige, which is the peak in the top right hand part of the photograph, and we're looking up the upper reaches of the Romanche Valley. There's the thrust, and it carries basement, crystalline basement, onto Jurassic shales, forming that sort of bandlands, gullied, ravined landscape lower on the hillside. So if we follow the structure from south, that's the right hand side of this image, towards the north, we can see that the thrust climbs section so that its hanging wall puts Jurassic rocks onto a footwall of Jurassic, and the edge of the basement comes down out of the sky, shown by that pecked yellow line. So the thrust is climbing section in its hanging wall from south to north. And that's how it works on the map. So thrust structures in the Ecrins stacking basement on cover, or indeed basement on basement, but as we go north, the same thrusts stack Jurassic on Jurassic rocks. So the northern edge of the Ecrins is marked by lateral ramps and this dramatic northward variation in thrust sheet content. So let's continue with this thrusting idea. So here's a cross-section that was put together by Jean Gurgel in the late 1940s. And he interpreted the basement, again shown here in pink, as being carried on a whole series of thrusts, stacking up many sheets of basement rocks. And if we take this cross-section at face value, we can measure around the tops of the basement sheets to get an idea of the restored section width and work out the shortening. And if you do this by unravelling the top of the basement, Gurgel's interpretation implies something like 64 kilometres shortening in the cross-section. But that's a very simple type of restoration. Let's consider the thrust sheet geometry in a bit more detail, which is what I did in the middle part of the 1980s. So here's my cross-section based on Gurgel's surface geology, showing how the thrust may work at depth. And the cross-section is drawn on the basis of using the thickness of the basement thrust sheets as measured down from the unconformity at the base of the cover to reconstruct a template. So here's what we do. We can measure the thickness of the basement thrust sheets from the unconformities at the top down to the thrusts that we interpret at depth, and we can rehang these onto a template. And here's that template, putting the basement cover contact horizontal and rehanging those measurements to find the restored position of the thrust. And you'll see that this implies that this particular thrust slice is defined by a thrust flat, a horizontal component, that then climbs a ramp. And I've numbered that thrust 15 on the restored section, so you can see which thrust is which from the restoration to the cross section. You'll notice that further east, behind those blue arrows, that there are many thrust slices that are much thinner, implying much higher level detachment of the basement slices. And that's shown on the restoration. Now, this restoration obviously assumes that the basement cover contact was originally horizontal and acts as a datum from which we can measure the thicknesses of the thrust sheets and hence define thrust geometry. So we're assuming that the top basement was horizontal, therefore that unconformity was essentially planar between cover and basement. But this restoration, as we've seen so far, is only representative of part of the cross-section we see at the top. Let's put in the rest of it. There. So the full cross-section at the top restores to that double length of template below, assuming this restoration approach. So we can establish the amount of shortening by comparing the distance in the final state section across the thrust structures, which is between points X and Y on the cross-section, and make an equivalent measurement on the restored section, and if we subtract the present day section from the restored section, we can of course calculate the change in section length, which is the shortening. Well, the present day cross-section width is 75 kilometers between X and Y. If we measure it on the restored section, which is this bit on top with the bit underneath, the total section length of the restoration is 252 kilometers, so we've got 177 kilometers shortening implied by this approach, which is a lot of shortening. That value is almost 3 times the amount that we calculated by the simple measurements using Gogel's original section. But is it appropriate? Critically, it assumes the top of the basement, that unconformity, was horizontal. It's critical for re-establishing the thrust trajectories. But was it? Well, let's go to the field. Here we are in the winter looking across part of the region towards the southwest, and I've picked out in the landscape a fault shown in red. And this fault has downthrown in this direction, so that on the far side of the fault we have a basement block, the so-called Typher Basement, and beneath that cloud cover in the valley are Jurassic sediments. In fact, they poke out to form that little hill that we can see between us and the fault. So it's a normal fault that down throws towards us in this viewpoint the Jurassic sediments. And these Jurassic sediments reside in something that's known as the Ornon Basin. So where are we? Well, let's come back to this basement map. We were here looking from the ski resort of Alpes d'Huez out across the Ornon Basin towards the southwest, towards the Typher Basement massif. And we were looking onto this fault structure here, which is called the Ornon Fault. And you can see the sense of downthrow shown by those bricks is down to the east, so that we have the light blue Jurassic sediments at outcrop in the Ornon Basin. It's not the only fault with this sense of displacement. There's another one here near La Mure, out there to the west. So let's look at a cross-section now drawn across this area in this orientation. And this cross-section is a restoration of the relationships between the basement and the Jurassic sedimentary cover. Here it is. The basement is in red. The Triassic rocks are shown in that sort of purpley colour on top, forming a thin veneer, and the Jurassic rocks are shown by those various blues and turquoise colours. The section runs from west to east, so that the basement blocks are bound by down to the east dipping normal faults. That's the Ornon Fault. And these fault blocks and their stratigraphies are capped by a once continuous panel of uppermost Jurassic limestones, Tithonian limestones, that would have formed the post-rift sequence that caps the syn-rift Jurassic strata. So let's go and have a look at the Ornon Fault close up. This is a really, really famous outcrop. We're looking north. The fault scarp is that cliff face that lies above the students working along the outcrop there. The outcrops on the left, the steep face there, and the pale rocks are the basement rocks in the footwall to the fault. That is the fault plane dipping down towards the students, and they're stood upon those shaly Jurassic sediments that form the hanging wall fill to the Ornon Fault. That fill continues across the valley, you can see that village in the background, and the slopes beyond it, which are the shaly Jurassic rocks of the Ornon Basin. Pretty spectacular. But what we're going to do now is stand back towards that village and look back onto the outcrop that everybody stood on here. And that's what that photograph is on the left. And so we're looking onto the fault plate. That big white scar is the fault surface that the students were stood at the foot of. So the fault comes across the foot of that scarp, but what's that large block in the middle? There. That green lump that I've picked out is a large block of Triassic volcanics. It's a large fallen block that is encased in the Jurassic sediment. In other words, it's a listolith that fell down the fault scarp as it was moving in the Jurassic, and it's frozen into the landscape to be found today. Really spectacular. So the Ornon fault was clearly active and controls the Jurassic geology. So let's step back to the cross section again, and we can see the Ornon fault there and its friend next door that divides the Typher from the Lamure block. And there are a series of subsidiary normal faults in here that formed during the Jurassic, associated with the rifting and formation of the European continental margin to Tethys. These are structures that existed before the Alps were formed. Now, remember, this cross-section we've drawn on top is a reconstruction of these faults before Alpine deformation. They now lie in cross-sections like this, and this is a section put together by Mike Coward and others in 1991 through the region. So for Coward et al., they see that the normal faults that were Jurassic in age play a pivotal role in the development of the Alpine deformation in the Tertiary. It's an inversion structural model. The faults are pinned and control how the basement and cover deform. A classic example of this is in the middle of this cross-section, where this is the outcrop. Notice the Jurassic sediments in here, and that hillside is the best part of 1 kilometre high. The Jurassic sediments are folded by upright fold structures and little thrusts. So we're looking north. The Ornon fault would lie to the left of this photograph, and we're looking at the deformed fill to the Ornon Basin in the hanging wall to the Ornon fault. So that's the situation before deformation in Alpine terms, and that's what we're looking at now. A crunched up half-graben. This type of deformation is known as buttressing, the idea being that the basin fill has been pushed up against the pre-existing normal fault, crumpled up against it, creating these upright structures. Indeed, this is the global type example of this style of deformation. So the normal faults in this type of interpretation play a pivotal role in controlling the structural style. We can take these ideas further and maybe consider a cross-section here that I put together in the late 1980s, which shows the idea that perhaps these normal faults reactivate at depth to control the location of the thrust front on the scale of the Alps here. So this is a Crustal Scale section. Highly speculative. Well, an alternative to this idea of simple thrust reactivation is proposed here by this cross-section by Belhazen et al. In 2012, which has pre-existing normal faults, but doesn't suggest that they play a particularly strong role in the deformation during Alpine times. Rather, that the crust is cut by shear zones that have thrust sense, shown by those darker bands, that simply restack the sedimentary basins that existed before thrusting. The notion that the basement is being restacked on entirely new thrust zones contrasts with an interpretation put together by Thierry Dumont a little bit earlier. So here's Dumont's cross-section across the region, and it shows pinched-in syncline types behaviours across here, but those pinched-in synclines are forming against the pre-existing normal faults. There are thrust faults in here, and many of these are located on pre-existing normal faults. And let's just look at a part of this cross-section in this region here, around the town of Bourg-d'Oisans. So here's Dumont's more detailed section in here. West is on the left, east is on the right, showing basement and the basement foliation picked out by those darker red streaks, and a granite within the structure as well. The Jurassic cover rocks are shown in those various blues and turquoise colours above. So for Dumont, the basement is penetratively deformed with a steep foliation. So it's not just a simple matter of the cover sediments being buttressed up against the pre-existing normal faults, but actually everything's being squashed through here. And we can just about recognise the sedimentary fill of the Ornon Basin and the next half graben to the east, the Mizoin Basin. And we can recognise these by looking at the stratigraphic pinch-outs against the basement. There are thrust structures in here that are of Alpine age, and there are also normal faults that have simply been inherited into this deformation, and here they are. And the normal faults have not been reused, they've just been steepened up by all this strain. Let's take some of these ideas and move towards a crustal model for the deformation of the Ekra. Here we're putting it in context across the rest of the outer part of the Alps. So the region out on the left with the coloured up strata in is the Vercors district of the subalpine chains. So let's just schematically put in the eroded parts of the inverted sedimentary basins that form the Ekra here. Okay, now let's go to crustal scale. So we'll step back a bit. Here's that cross section, and I've drawn the moho in underneath this that's been determined geophysically. We can take that moho that defines the base of the crust and it inclines to become deeper beneath the Ekra. And I've just cartooned a trajectory for the frontal thrust. Now, what we want to try and do is to restore these sedimentary basins onto a template. Now we're going to assume that the cross-sectional area of basement that we see on the cross-section today is the same as that existed before the Alpine shortening. So in other words, we can create an area restoration of the crust. And here it is. In doing this, I've had to assume a particular amount of shortening. It's 55 kilometres, as I've defined it in here. Is radically less than the 177 kilometres that we got for the restoration if we assumed that the top basement structure was horizontal. The reason that we can get away with this lower amount of shortening is because the basement cover contact is not planar and horizontal but cut by normal faults, which creates a more complicated geometry. Changes the restoration. We can't use the shape of the top basement to define thrust trajectories as we did at the start of this presentation. So there's a restoration. The question is whether it's appropriate or not. Well, in this restoration, we've taken the Dumont ideas that the crust is just simply shortened by penetrative deformation and some localized thrusting. The normal faults have not been reused. We've retained cross-sectional area. We've just thickened the crust in this more distributed, ductile fashion. The idea that the normal faults have not been reused is based on the recognition that structures like the Ornon fault are still in net extension. But that is a false assumption. Just because the normal faults are in net extension doesn't mean that they've seen some contractional displacements. It's just that the original normal fault throw has not been fully recovered by the contractional tectonics. So in fact, the shortening could be considerably more than 55 kilometres. So I've just changed the restoration to this sort of geometry. Again, the cross-sectional area for the crust is the same in all these diagrams, but the length of the restored section I've increased, and in order to do that, I've suggested that the normal faults have had a greater throw originally, and that some of this throw has been recovered and reactivated by contraction. They're still in net extension to a large part, but it doesn't mean that they haven't reactivated a little bit in contractional tectonics. And if we do this, we can get a probably more realistic crustal thickness geometry across here and a implied shortening of about 85 kilometres. And we can juggle between these, trading off the crustal thickness on the restored section to the amount of shortening. If we invoke a thinner continental crust, then we need to imply a greater amount of tectonic shortening of contraction during the Alpine orogeny to create the crustal thicknesses that we see today in the top cross section. A way of calibrating this would be to look at the substance history of the sedimentary basins such as the Ornon Basin, though this is rather difficult given the preservation state of the stratigraphy there. Okay, so that's the Ecrins, but it's by no means unique in recording this style of deformation, particularly the presence of pre-existing normal faults. Let's move around the Alpine arc into Switzerland and to the R massif. And the front of the R massif contains stacked Jurassic strata, the basin fill to potentially pre-existing normal faults. Perhaps the most spectacular illustration of this is the mountain of the Eiger. And here's a cross-section through this sort of region drawn by Léon Collet in the 1920s. And this has no particular interpretation or agenda associated with it. It simply records a first pass interpretation of the various parts of the Mesozoic successions in here, the Jurassic in blue, the Cretaceous in various green colours, and the Triassic, what we would now call pre-rift succession, lying directly on the basement that's in pink. Well, that's one cross-section. Here's another, just along strike. Again, the basement in pink, the Triassic in mauve, the Jurassic in blue, and the Cretaceous Tertiary in green and yellow, respectively. Well, let's look at this cross-section because it shows pinched-in pieces of basement and cover beneath the summit of the Wetterhorn and on the adjacent hillside that gives us an idea of the deeper structure. Now, it's tempting to consider basement climbing over sedimentary cover like this to be due to thrusting, something like this. So let's look at this top structure and ask ourselves whether this is potentially a thrust. Well, critically, look at the preservation of what would be the Trias within that pinch of Jurassic. The thrust model would say that the overhanging basement contact would be the thrust and therefore would not have Triassic on it, and the Trias would be retained on the lower side of the synform. Well, let's look at the outcrop above on the Wetterhorn, and we see the opposite is the case. The steep side of the synform has got a veneer of Triassic cover that keeps the Jurassic away from the basement, and it's the underside, the lower limb of the synform, that misses the Triassic. So a thrust model does not explain the stratigraphic relationships in that fold. These are not compatible geometries. An alternative is that this is a folded and buckled version of an array of pre-existing normal faults. If you take the area identified on the cartoon below within that ellipse, you can see that if that half graben became tightly folded and inclined, the left hand or lower limb of the syncline would be the trajectory of the old normal fault and therefore would not have Triassic pre-rift on it, and the right hand or overhanging limb of the synform would have the unconformable Trias on there, which is what we see on the Wetterhorn. So maybe these pinched-in structures along the front of the R massif are buckled normal fault structures. So perhaps this is a common structural style for the external basin massifs as a whole. Let's return to the Ecrins. And to summarise, we're suggesting that the Ecrins is the surface expression of thickened continental crust, and that crustal thickening has been accommodated by fault reactivation initially of the normal faults, but then overprinted by distributed strain that deforms the basement penetratively. So let's take that idea and think about reactivation of pre-existing structures in mountain belts, which we've sort of cartooned up in this diagram. The frontal structure here may involve simple inversion. In the Alps, to begin with in the Ecrins, that's what happened. And it certainly happens in many sedimentary basins away from the Alps. In considering simple inversion structures like this, let's consider a strength-depth profile in an idealized sense. So, if we imagine the continental crust to be relatively strong, then pre-existing weak faults will control the deformation. Certainly while they remain at low angle. Of course, an initial array of normal faults that are encountered in contractional tectonics may have been relatively gently dipping, but as they reactivate they will steepen, and as they steepen they'll have a reduced propensity to reactivate as a thrust, unless of course the displacements are oblique. So it's hard to generate thick crust through simple reactivation. And in any event, it doesn't seem to be what's happening in the Ekra. What about the distributed strain? Well, let's consider this area here, where the basement is straining and there's buttressing against faults. The fault zones may well be weak, but the basement is potentially weak as well. We've seen that it consists of an array of different materials. It's not just a felspar-rich granitic crust. There are metasedimentary packages in here. There's all sorts of other materials, which may be significantly weak. In other words, the pre-existing faults may not be significantly weaker than the surrounding basement. So there may be reactivation, but there'll also be penetrative strain through the rest of the crust. So we need to understand what the crust is made of before inferring too much about whether reactivation will occur. This is the style that seems to be appropriate for the Ekra, potentially for the R massif, and maybe for other basement massifs within the external part of the Alps. So we need to shed light on the nature of the crystalline basement if we are to forecast how the continental crust deforms as it goes into mountain belts. The external basement massifs of the Alps give us this insight.